Okay. Okay. Let me check. Okay, sorry for the delay. Let's get started. Welcome to the last background lecture of this semester's Modern PNSSD course. In this research session, the second research session, we will cover the recent exciting works done in the software research group. Okay, and this is the outline of today's research session. So first, we will cover the technique called GenStore, which is an in-situ processing technique for accelerating and improving the energy efficiency of genomics applications. And after that, we also introduce the Sybil, reinforcement learning-based hybrid storage system management. Okay, so let me briefly introduce today's presenters. So the first presenter is Nika Mansourighiasi, who is a PhD student in software research group, and Nika earned a master's and a bachelor degree from ETH Zürich and University of Tehran, respectively. And Nika's research interests lie in computer architecture, a broad range of computer architecture, and emerging technology for future computer architecture, and also bioinformatics. Okay, so Nika, if you are ready, please start. The stages are yours.
Thank you very much, Jason, for the introduction. So let me share my screen. Is the screen shared correctly?
Yes, I can see your screen. First, the page of slides.
Okay, and then let me, does that move also? Does the slides, did it move?
Yeah,
okay.
Yes, looks fine, thank you.
Okay, sure. Then let's get it started. Just give me a second, okay. Okay, so hello everyone. I'm going to talk about GenStore, a high performance and storage processing system for genome sequence analysis. Genome sequence analysis is critical for many applications. Sorry, the clicking has some problems, sorry. Yeah, okay, it's critical for many applications such as personalized medicine, outbreak tracing, and evolutionary studies. And genome sequencing machines extract the smaller fragments of the original DNA sequence known as reads. Read mapping is the first key step in genome sequence analysis that aligns reads to potential matching locations in the reference genome. And for each matching location, the alignment step finds the degree of similarity and differences between read and reference by calculating the alignment score. Calculating the alignment score requires computationally expensive approximate string matching, or ASM, to account for differences between reads and the reference genome that might occur due to different reasons, such as sequencing errors or genetic variations. Read mapping performs alignment on large genomic datasets containing millions of reads. Therefore, read mapping is both computationally expensive and incurs high data movement overhead from storage. There has been significant effort into improving read mapping performance through efficient heuristics, hardware accelerators, and various filters that prune reads that do not require expensive computation. While these approaches address computation overhead in read mapping, none of them alleviate data movement overhead from storage, whose impact becomes even larger when a computation overhead gets alleviated. Our key idea is to filter reads that do not require expensive alignment computation in the storage system to fundamentally reduce data movement overhead of read mapping. Examples of reads that do not require the costly alignment step are exactly matching reads, which are reads that match exactly to the reference genome and do not need approximate string matching performed during alignment. And the second example of reads are non-matching reads that have no potential matching locations in a reference genome and hence can skip the alignment step. However, filtering reads in a modern SSD can be challenging due to different behavior across read mapping workloads and limited hardware resources available inside the SSD. By addressing these challenges, we propose GenStore, which is the first in-storage processing system designed for genome sequence analysis to reduce both computation and data movement overhead. GenStore provides high performance and energy benefits compared to state-of-the-art hardware and software baselines. So that was a summary of my talk. So let's start with the background on read mapping so we can dive into the talk in more detail. Mapping reads to a reference genome requires expensive computation on large data sets, and the search space in the reference genome can be very large. For example, for human reference genome, it can contain more than 3 billion characters. So therefore, read mappers typically use an index of the reference genome to reduce the search space. So this index contains unique K-length subsequences called k-mers extracted from the reference genome and the location of these k-mers in the reference genome. Read mapping is a 3-step process, and state-of-the-art read mappers involve several heuristics to reduce the cost of expensive alignment computation. In the first step, which is called seeding, sorry, I think I disconnected a little bit. Is it connected right now?
No, I have no problem.
Okay, good. It gave me a sign that my internet might be weak. Okay, cool, thanks, sorry. So in the first step, which is called seeding, the mapper determines the potential matching locations or seeds in the large reference genome to see where the read could potentially map. And to do so, it generates k-mers from the read and looks up the k-mers in the index. And for the k-mers that actually hit in the index, it marks the location of those k-mers in the reference genome as potential matching locations or seeds. Then, to further reduce the cost of this computationally expensive alignment, the read mapper performs a second step, which is called chaining or seed filtering, in which the mapper prunes the seeds in the reference which would not align using a simple approximation of the alignment score. So we further reduce even the search space in that reference genome that we've already marked in the first step. So the reads that have all their potential matching locations or seeds filtered in this step skip the alignment step. Otherwise, the third step called alignment performs executes to determine the exact differences between the read and the reference genome. And does so using approximate string matching, which was the computationally expensive step. So we perform experimental studies to understand the potential of efficient in-storage filtering for improving read mapping performance. We perform a case study on real-world genomic read datasets on various read mapping systems and state-of-the-art SSD configurations. And we make several observations. First, the ideal in-storage filter significantly improves performance by reducing the computation overhead and data movement overhead. Second, filtering outside SSD relatively performs lower performance benefit because it does not reduce data movement overhead from storage, and it also must compete with read mapping for other system resources. And finally, we observed that a hardware accelerator reduces the computation bottleneck, which makes I/O even a larger bottleneck in the system, which in turn necessitates developing in-storage filters. So motivated by these observations, our goal is to design an in-storage filter for genome sequence analysis in a cost-effective manner. So we have 3 key objectives in designing our new systems. First, the system should provide high in-storage filtering performance to overlap the filtering with the read mapping of unfiltered data. Second, the design should support reads with different properties and different degrees of genetic variation. And third, it should not require significant additional hardware overhead inside the SSD. So to this end, we propose GenStore, which is the first in-storage processing system designed for genome sequence analysis. And our key idea is to filter reads that do not require alignment inside the storage system and send the unfiltered data to the host system for further processing. However, filtering reads in a modern SSD can be challenging due to different behavior across read mapping workloads and limited hardware resources available in the SSD. So let's take a look at filtering opportunities based on the features of the input reads. So sequencing machines produce one of two kinds of reads: short reads that are highly accurate but shorter, so up to a few hundreds of DNA characters, and long reads that are less accurate but longer, for example, from hundreds to millions of DNA characters. Based on these, we leverage two filtering opportunities. First, we can filter exactly matching reads, which are reads that match exactly to one or more subsequences of the reference genome and do not require approximate string matching during alignment. Exact matches can frequently occur in short and long read sets with low, they can occur in short read sets that have low sequencing errors and also low genetic variation. Second, we can filter non-matching reads, and such reads do not have any potential matching locations in the reference genome and can therefore skip the alignment step. So such reads can frequently occur in long read sets, which have high sequencing errors, and shorter long read sets that have high degrees of genetic variation. So by thorough analysis of the read mapping process, with different for reads with different properties and different degrees of genetic variation, we designed two low-cost in-storage filters: GenStore EM for filtering exactly matching reads, and GenStore NM for filtering most of the non-matching reads. So let's take a closer look at GenStore EM. GenStore EM accelerates read mapping by using an efficient in-storage filter to filter reads that have at least one exactly matching location in the reference genome via simple operations and without requiring alignment. But the key challenge in designing GenStore EM is the large number of random accesses to large data structures inside the SSD. So this is challenging because of two reasons. First is that NAND flash memory exhibits poor performance for random access reads, and there is limited DRAM capacity available in the SSD, which is relatively smaller compared to the size of the data structures that need to be randomly accessed. So to reduce the number of accesses per each read, we introduced read size k-mers. Therefore, instead of extracting several k-mers per each read and performing index lookup for each of them, we can use the whole read as one k-mer and have only, therefore, one index lookup per read. So to avoid random accesses to the index, we introduced the sorted index of read size k-mers. And this sorted index allows finding exact matches via sequentially scanning the read sets and the index. Now I show the key idea of GenStore EM with a simplified example in which the short read contains tens of characters. Please note that, as I mentioned, short reads can contain actually a few hundred characters, but for the sake of simplicity, I'm showing read with 10 characters. Suppose that we have two data structures: a sorted read table, each entry of which stores a read and its unique ID, and a sorted k-mer index, which contains all unique read size k-mers of the reference genome, along with each k-mer's corresponding location in the reference genome. And each data structure is sorted by read and k-mer in alphabetical order. So we sequentially scan through these data structures in three different ways based on the comparison result of the current read and k-mer. First, when the current read and k-mer are identical, we record the read as an exactly matching read that can be filtered from further read mapping process. And then we move to the next element in both arrays. So if the read is alphabetically larger than the k-mer, we conclude that the k-mer does not match any read because we've been sequentially scanning it so far. And then we go to the next element in the index so we can examine the next k-mer. And then if the k-mer is alphabetically larger than the read, we conclude that the read does not match any k-mer in the index. So it needs to be sent for full read mapping process. And then we go to the next element in the sorted read table so we can examine the next read. So using this technique, GenStore EM avoids random accesses and performs filtering using only simple low-cost logic. Despite the key benefits of the sorted read-sized k-mer index, this index lookup takes data structure takes a large space. So for example, 126 gigabytes for human index, due to the large number of unique read-sized k-mers. So we further reduce the overhead of GenStore EM by replacing these read-sized k-mers with a strong hash value of the read that can act as the sorting criterion and the fingerprint of each entry. So using a strong hash values instead of read-sized k-mers reduces the size of this index by 3.9 times. While this index is still larger than the baseline k-mer index using the conventional read mappers, our proposal is feasible for storage processing due to the large capacity and high internal bandwidth of modern NAND flash-based SSDs. Now I show the overall operation flow of GenStore EM with sorted read table and sorted k-mer index in the NAND flash memory, distributed across all channels and dies, so that we can leverage the full internal bandwidth of the SSD. And then we have this comparator logic also located on the SSD controller. GenStore EM consists of two steps. Step one reads the two data structures from the NAND flash chips to the SSD's internal DRAM in the batched manner, and stores these small batches in DRAM. And step two performs exact match filtering within each batch using simple comparator logic, and sends the unfiltered data to the host system. So step 1 and 2 are performed in a pipeline manner. During filtering, GenStore EM sends the unfiltered reads to the host system for full read mapping. So now let's take a closer look at GenStore NM. Using chaining, GenStore NM filters most of the non-matching reads, which are reads that would not align to any subsequences in the reference genome. Recall that chaining filter calculates a similarity score for each read called chaining score, and filters reads that do not have any high scoring potential matching location in the reference genome, and therefore skips the third alignment step. So so calculating a chaining score in the SSD can be challenging because finding the best chaining score requires performing many iterations of a dynamic programming algorithm for all seeds within a read, and they can be potentially challenging for long reads since they have a large number of k-mers per read. So to reduce the cost of chaining, GenStore NM uses a lightweight chaining filter that selectively performs chaining only reads with a small number of seeds and directly sends reads with that would require more complex chaining to the host system for full read mapping. So this idea is based on our key observation from analyzing a wide range of real-world genomic data sets. So this figure is showing the alignment probability of a read in a long read data set to subsequences in the reference genome as a function of number of seeds per read. So in the x-axis, we see the number of seeds per read, and we'll see for each read that has that number of seeds, how much would be the alignment probability, basically. So we observe that reads with sufficiently large number of seeds are very likely to align to subsequences in the reference genome, and such reads can be directly sent to the CPU for full read mapping and bypassing the in storage filter. We can conclude that such selective filtering, which is much more lightweight than the full chaining approach, can filter many non-aligning reads without costly hardware resources in the SSD. And for more details about GenStore NM's implementation, please refer to our paper. So I will now go into our results. So we evaluate the following systems: base, which refers to the state-of-the-art software or hardware read mappers for both short and long reads, and GS, which is base, whatever even hardware or software base integrated with the GenStore inside the SSD. So we evaluate these mappers and systems with various SSD configurations, a low-end, a medium-end, and a high-end SSD. For other details about our methodology, please refer to our paper. So we analyze the benefits of GenStore EM for a 22 gigabyte short read set, where 80% of reads exactly match some subsequences in the reference genome and can be filtered. So that commonly is like a range that on average human reads would exactly match the reference genome. So that's a human data set. So we show the benefit of GenStore on software and hardware read mappers, and we show that GenStore provides up to 2.5 times speed up compared to the software baseline, and up to 3.3 times speed up compared to the hardware baseline. And it provides up to, on average, 3.92 times energy reduction. So we analyzed the benefits of GenStore NM for a 12 gigabyte long read set with very high degree of genetic variation compared to the reference genome, where 99.7% of reads do not match any subsequences in the reference genome. And we show the benefit of GenStore on software and hardware read mappers. And we show that it provides up to 27.9 times the speed up compared to the software baseline, and up to 19.2 times the speed up compared to the hardware baseline. And it provides on an average 27.2 times energy reduction. We find area and power values of GenStore by synthesizing GenStore EM and NM using 65 nanometer technology node, and find that for an 8-channel SSD, the area of GenStore is 0.2 millimeters square and the power is 26.6 watts. By scaling the area to lower technology nodes, we observed that the area overhead of GenStore is 0.006% of an Intel processor and less than 9.5% of the 3 ARM processors in a SATA SSD controller. Let me briefly talk about other results that are included in the paper before concluding the talk. So these results include the following. Effective read set features on performance. For example, we sweep the data set size up to 440 gigabytes, and filter ratio, basically how many percent of reads in a read data set can be filtered. And we also analyze the performance benefit of an implementation of GenStore outside SSD. So in some cases, we observed that it provides performance benefits due to more efficient streaming accesses, but it provides significantly lower benefits compared to GenStore implementation inside the SSD. We also provide more detailed characterization of non-matching reads across different read mapping use cases for different species. Now, let me conclude the talk by giving the summary. There's been significant effort into improving read mapping performance through efficient heuristics, hardware accelerators, and various filters that prune reads that do not require expensive computation. While these approaches address the computation overhead in read mapping, none of them alleviate data movement overhead from storage, whose impact becomes even larger when the computation overhead gets alleviated. Our goal is to improve the performance of genomic sequence analysis by effectively reducing unnecessary data movement from storage system. And the key idea is to filter reads that do not require the expensive ASM computation in the storage system to fundamentally reduce data movement overhead. However, filtering reads inside SSD is challenging because read mapping workloads can exhibit different behavior and there are limited available hardware resources in the storage system. And to this end, we propose GenStore, the first and storage processing system designed for genome sequence analysis to reduce both computational and data movement overheads. So GenStore provides high performance and energy benefits compared to state-of-the-art hardware and software baselines. So thank you very much for listening. And yeah, if you have any questions. Yeah.
Thank you, Nika, for a nice presentation. So we have some people in our YouTube live streaming. So do you have any question, people there? Yeah, the presentation must be very clear, I think. Yeah, so I have no technical question, because I'm also a second author of this paper. But as your lead of this first in-storage processing system, for genome sequence analysis, I have a question. So I would like to ask your opinion regarding the in-storage processing, meaning our scheme, including our scheme and the advancement now, meaning technical advancement now is happening in genomics applications. So, for example, as far as I know, there are also significant effort to make the reads more accurate and longer, right?
Yeah.
So so do you think our technique can be also useful in the future, where such a new read sequencing technology appears?
Yeah, thank you very much for the question. So yeah, as you mentioned, there's been like significant effort into having longer and more accurate reads. For example, hi-fi reads that are being developed. So there are different aspects to it. If a read again shows high degrees of genetic variation, again, it can be filtered with techniques that are proposed in GenStore and M that filter non-matching reads. However, if the reads do not show high degrees of genetic variation and also at the same time don't have high sequencing errors, then we would expect that there would be not many or like large fraction of non-matching reads, and therefore ideas of GenStore and wouldn't directly apply. And also GenStore EM works for shorter reads. So definitely it is important to develop techniques for filtering reads or like reducing data movement overheads from storage for such sort of reads. And as you know, this is also one of the aspects that we've been looking at, which is definitely like important to be followed. However, we think that some of the common let's say guidelines or design decisions made here to solve a specific challenges can be also applied there, but definitely the design itself needs to be expanded to cover such sort of reads, as we currently are looking into it also.
Great. Yeah, thanks for the answer. It makes there a lot of sense.
Thank you very much.
Okay, yeah, if we don't have any further question, so we can move on to the second presentation. Thank you again, Nika. And by the way, I don't know, I'm not sure if we properly clarified this. This paper was presented first in ASPLOS 2022. So, and yeah, I would encourage, so there are, as Nika explained, that there are a lot of more interesting materials, including the analysis, motivation analysis, and also more rigorous evaluation results, and also discussion. So I would encourage you read the full paper if you're interested in.
Yeah, and please reach out if you have something to discuss. We look forward to that. Yeah.
Great, great. Thank you, Nika.
Sure,
so
thanks.
Let me share my screen again. I think you can see my screen, right?
Yes.
Okay, so our second oh, sorry, I should change the name. I forget to change his name. Sorry, well, let me, give me some time. Okay, what is happening? Let me share my screen again. You can see my screen, right?
Yeah.
Okay, sorry about that. So our second presenter is Gagandeep Singh. He's a postdoctoral researcher in Software Research Group, and he earned his PhD degree from TU Eindhoven, which was a collaboration with IBM Research at Zürich. And his research interests lie in computer architecture and with a focus on machine learning and hardware acceleration. So, okay, so Gagan, are you ready for presentation?
Yes, Jason, I'll share.
Thank you.
Can you see the screen, right?
Yes.
Okay. Thank you very much, Jason, for the introduction. So, hello, everyone. Today, I'll present a recent paper, which was published in ISCA 2022. So just recently, like a month back. And the paper is called Sybil, which is an adaptive and extensible data placement in hybrid storage systems using online reinforcement learning. First, I'm going to start with an executive summary. hybrid storage systems use multiple different storage devices to provide high and scalable storage capacity and high performance. We observed two key shortcomings in prior data placement techniques. First is the lack of adaptivity to workload changes and changes in device types and configuration. Second, they also lack extensibility to more devices. So in this work, our goal is to design a data placement technique that provides both adaptivity by continuously learning and adapting to the application and underlying device characteristics, and also easy extensibility to incorporate a wide range of hybrid storage configuration. To this end, we propose Sybil. Sybil is an online reinforcement learning-based hybrid storage system that provides both adaptivity and easy extensibility, and also provides ease of design and implementation that requires only a small computation overhead. We extensively evaluate Sybil on real systems using a wide range of workloads, and we show that Sybil outperforms prior data placement techniques by 21.6% in a dual hybrid storage system, and up to 48.2% in a tri-hybrid system. And Sybil achieves 80% of the performance of an Oracle policy that has complete knowledge of the future access pattern, while incurring a storage overhead of only 124.4 kilobytes. And we open source our code on our GitHub repository. So this is the outline of the talk. First, I will go into discuss the key shortcomings of prior data placement techniques. Let's look at some basics of hybrid storage system. Over here, we have a typical hybrid storage system consisting of fast yet small storage device and a slow yet fast storage, a large storage device. And the address space is divided into a number of logical pages, for example, 4 kilobytes, which are assigned to an application. There is a storage management layer in the OS, which orchestrates the host input-output requests across heterogeneous devices. The storage management layer is also responsible for data migration between the storage devices. So to move the data from the fast device to the slow device is called eviction, or from moving from the slow device to fast device, which is promotion. And to do that, the storage management layer has to take into account the hotness or the coldness of a page. And so a desirable policy has to effectively utilize the low latency characteristics of the fast device while making optimal use of its small capacity, and should also be extensible to a wide range of workloads and hybrid storage configuration. So therefore, the performance of a hybrid storage system highly depends on the ability of the storage management layer to effectively manage diverse devices and workloads, which is quite a challenging task. So therefore, we observe two key shortcomings in prior data placement techniques that significantly limits their performance improvement. First is the lack of adaptivity, both to the workload changes and changes in the device types and configurations, and also lack of extensibility when we extend our hybrid storage configuration to more devices. First, let's look at the lack of adaptivity to workload changes. We observed that prior data placement techniques consider only a few workload characteristics, which are statically tuned. And the designers believe that this is going to work for all different workloads, which is not really true for all the cases. Over here, we show average request latency of 4 sample workload for a policy called CDE, which is state-of-the-art heuristic-based policy. And we also show an RNN-based policy, which is a supervised learning technique. And we compare these policies to an impractical Oracle, which has the knowledge of future input-output access patterns. So this is the best we can achieve. So the lower the latency, the better it is. And we observe that all of the baselines provide reasonable performance under specific workloads, while for others, they show very lower performance than Oracle. And on average, we observe a performance loss of up to 41.1% compared to Oracle. We conclude that because we don't really take into account all the characteristics of workloads, that's why we have this performance gap. Second, we also have lack of adaptivity to the changes in device types and configurations, because we don't really consider the underlying device characteristic. Example, the change in level of asymmetry in terms of read and write, or the effect of garbage collection. For example, in this figure, we show again the 3 policies. And in addition, we have another policy, which is an extreme case where everything is placed in the slow storage, which we refer to as slow only. we observed that the performance of some workload is even worse than slow-only policy that places everything in the slow storage. While if we take another configuration of these workloads on a different device configuration where we have different hybrid storage system, they might provide better performance than slow only, because these policies are really trained for, or they are built for these kind of configuration and not for a different configuration. Therefore, we conclude that the high diversity in device characteristics makes it very difficult for a system architect to design a generic data placement techniques that is suitable for all hybrid storage configuration. And then there's an issue with extensibility as well, because most of the design techniques are rigid that require significant effort to accommodate more than 2 devices, and they are usually built for just 2 devices. So if we have to extend a dual hybrid storage configuration to a tri-hybrid configuration, then we would have to design a policy from scratch to take into account all the different characteristics. For example, eviction, promotion from the new storage, and update. We would have to update the policy accordingly. So there's a lot of engineering and a lot of effort from the system architect in extending the prior data placement techniques. And this wastes a lot of precious design time and human resources. So in this work, our goal is to design a data placement mechanism that can provide both adaptivity by continuously learning and adapting to both the application and underlying device characteristics, and also easy extensibility to incorporate a wide range of hybrid storage configuration whenever we modify any device. So to this end, we propose Sybil, which formulates data placement in hybrid storage system as a reinforcement learning problem. Let's go into the formulation of data placement as a reinforcement learning problem. First, let me briefly describe the basics of reinforcement learning. In a reinforcement learning, there is an RL system which consists of 2 components. There's an agent and an environment. The agent observes the state of the environment in every time step and takes an action based on the state. And for every action, it receives a reward, which is kind of a feedback from the environment to tell how good or bad the agent is performing. And the agent's goal is to find a policy where whenever it takes an action in a given state, it will get the maximum rewards. That's the agent's goal. So if we have to formulate this data placement as a reinforcement learning problem, we have Sybil, which acts as the agent, while the hybrid storage subsystem acts as the environment. Sybil observes the workload and system features for every storage request and uses as a state information to take a data placement action. And for every data placement action, Sybil receives a numerical reward that evaluates the effectiveness of the data placement decision. And now we will concretely define the state, action, and reward for Sybil. So let's look at the state first. For the state, we use limited number of state features after performing a proper feature selection, because it helps us to reduce the implementation overhead. And we also observe that RL agent's performance is more sensitive to the reward than the state features. So adding more features does not really help in the state. So we define the state feature as a 6-dimensional vector of program features. For example, we take the size of the request, the type of the request, etc. And then we also quantize the state representation into bin to reduce the storage overhead, because if we have more of these features, then it will increase the state space as well. And for the reward, we define the objectives, which is the objective of the Sybil. So it could be anything. We could have like performance or energy consumption, etc. But in this work, we show the performance of Sybil by using objective as the request latency. So we wanted to minimize the request latency. And this request latency also encapsulates 3 different aspects, which is the internal state of the device. For example, whether it's a read or write request, or whether there's some internal process going on, for example, a garbage collection. It also encapsulates throughput. And also, like the way we formulate our reward, it also takes into account the amount of evictions that are happening from this fast storage. So we wanted to minimize that as well, so that our agent is more proactive. And we provide more details in the paper. And for the action, we define action as the selection of a storage device to place the current page. And such an action allows us for easy extensibility to any number of storage devices. So if we want to extend the action to like try hybrid system, we will just add a new action. And it makes Sybil learns to proactively evict or promote a page from the storage devices, which is also one of the goals which we wanted to achieve. Now I will provide a brief overview and design of Sybil. First, we discuss the execution model for Sybil. We implement Sybil in the host operating system, where for every storage request, Sybil uses an RL decision thread to make the data placement decision. While it's making its decision using the RL decision thread, there's another thread which is running in the background. It keeps collecting the information about the Sybil state and action and reward, which is used to train a data placement policy in the background. And periodically, we replace the RL decision thread policy with the RL training thread policy. Since our threads are running asynchronously, it avoids that the training in the RL training thread interrupts the delays of data placement decisions for the incoming request, which is happening in the RL decision thread. Now I will go into the implementation of each thread. First, let's look at the RL decision thread, where we have Sybil that decides the data placement for the current storage request while collecting the information about its decisions. For every new storage request to the hybrid storage system, Sybil uses the state information to make a data placement action. There, we have an inference network that predicts the expected benefit of each action for a given state. Sybil policy selects the maximum of the highest expected benefit, or it can select a random action for exploration. So in reinforcement learning, we always have this trade-off between exploration and exploitation, which is a hyperparameter as well. While making the data placement decisions, Sybil collects the information about the state, action, and reward in an experience buffer. And this experience buffer is used in RL training thread. And in the RL training thread, the collected experiences are used to update a decision-making policy of a different training network. So therefore, like Sybil is continuously learning from its past decisions and their impact. And these two threads are running asynchronously. And therefore, we are able to enable a parallel execution of the two threads where we duplicate the neural network that is used to make data placement decisions. So in the two threads. And so therefore, the inference network does not really have a separate training step. We just copy the weights of the training network periodically. And that's why these two threads are running asynchronously from each other. Now I will present our key results. We perform real system evaluation for both dual hybrid and tri-hybrid system, where we show over here we are showing our evaluation setup that consists of multiple different devices. We implement Sybil in the storage management layer with AMD Ryzen CPU. First, we evaluate a cost-oriented hybrid storage configuration in which we have a high-end SSD and a low-end SSD, where the latency difference between the two devices is quite large. And then we also evaluate a performance-oriented hybrid storage configuration, where we have a high-end SSD with a middle-end SSD, where the two devices have a bit comparable latency, but still there's a difference between the latency of the two devices. So, and we use 18 different workloads for MSR Cambridge and File Benchmark Suite, and compare Sybil against 4 state-of-the-art policies, which comprises of both heuristic-based policies and also supervised learning-based policies. First, let's discuss the results on cost-oriented hybrid storage configuration. Over here, we have the performance results in terms of average request latency for MSR Cambridge workloads and for all the different workloads and all the policies. We observed that Sybil consistently outperforms all the baselines for all the workloads for this specific configuration. And if we go to a performance-oriented hybrid storage configuration where the two devices have kind of similar latency, we observe Sybil still provides 21.6% performance improvement by dynamically adapting its data placement policy compared to other policies. But we observe there are like 2 workloads where Sybil provides a bit lower performance compared to some of the policies. And we observe that these workloads are really write intensive and have many random requests in terms of both excess patterns and the request sizes. Therefore, we show in the paper how we can overcome such kind of issues. And in such kind of issues, we need to do frequent retraining of the training network. And then Sybil is able to provide better performance in these cases as well. On average, Sybil achieves 80% of the performance of an Oracle policy that has complete knowledge of the future excess patterns. And we also evaluate a the extensibility of Sybil to more devices. So as I mentioned before, if we wanted to extend Sybil from more than 2 devices, what we have to do is we have to add a new action in the action space, and we added the remaining capacity of the new device as a state feature so that the agent knows how what's happening with the new device capacity, whether it's full or not. That's it. We didn't really have to do anything, and Sybil automatically figures out the best policy. So it reduces a lot of system architects' burden. Over here, we show the performance results for a state-of-the-art heuristic-based policy. This policy is actually an extension of the CDE policy, which actually requires significant effort to implement for handling all the data placement cases when we added the new device. And if we look at here, the comparison with the Sybil for tri-hybrid system, Sybil outperformed this state-of-the-art policy by up to 48.2%. Therefore, we conclude that Sybil provides ease of extensibility to new storage system configuration, which reduces system architects' burden in designing sophisticated data placement mechanism. And all of these Sybil's benefits come at a modest cost of 124.4 kilobytes of total storage, which is used for experience buffer, inference network, and training network. And our network is quite small. There are just 2 hidden layers which are fully connected. And we use like 40-bit metadata overhead per page for state features. And so in the end, we don't really need a really big network as well to do the prediction for the state features. And we have an inference latency of 10 nanoseconds, which is orders of magnitude smaller than the input-output read latency of even a high-end SSD, which is around 3 microseconds, for example, for Samsung NAND SSD. And the training of the network takes latency of 2 microseconds. And since I mentioned the training and inference are happening asynchronously in the background, so it's not really a problem for making a data placement decision. So in the end, Sybil provides a small area and inference overhead, which also satisfies the prediction latency for making a data placement decisions. We have many more exciting results in the paper, including the throughput comparison, evaluation on unseen workloads, evaluation on mixed workloads. And we also evaluate like different features when we try for the state vector. We also have effects of different hyperparameter values and how we tweak the values for Sybil. We also show the sensitivity to fast storage capacity if we have like limited fast storage, or if we increase the storage capacity, how Sybil performs on that. And we also try to provide explainability and analysis for Sybil's decision making, that why Sybil is doing what it's doing. So I would really recommend to go further and read our paper to know more about these results. And now I will conclude my talk. We introduced Sybil, which is the first reinforcement learning-based data placement in hybrid storage system that provides both adaptability and easy extensibility. And moreover, it also provides ease of design and implementation. We evaluated Sybil on real systems using many different workloads, and we showed Sybil improves performance by 21.6% compared to the best prior data placement policy in a dual hybrid storage configuration. And in a tri-hybrid hybrid storage configuration, Sybil outperforms state-of-the-art policy by 48.2%. And Sybil is able to achieve 80% of the performance of an impractical Oracle policy, which has a knowledge of future excess patterns with an overhead of only 124.4 kilobyte. We open source our code on our GitHub repository. I would recommend you to go and try it out. Thank you, and I'll be happy to take any questions.
Thank you, Gagan. So people in YouTube, do you have any question? Yeah, doesn't seem so. So, okay. For this work as well, because I am a co-author, I have no question regarding the technical stuff itself, but because you are the most expert in hardware acceleration, also machine learning. Yeah. So I would like to ask your opinion about the general reinforcement learning and reinforcement learning for system decisions, for example. So we use to provide the reasonable latency to inference speed and training speed, we use a dedicated GPU, right? Yeah, but yeah,
No, we use CPU in this case, actually.
Oh, so meaning that the inference, even if we use the deep RL technique, we don't need any GPU and a CPU, right? Any strong GPU, you mean, right?
Yeah, so there are like multiple things to it. So evaluate it using GPU, but we have to always consider it's not really always true that the GPU will be faster if we run our neural network there, because it depends on how big your model is. So I mentioned the model is really small, and how things work in RL is like when you're collecting your data set, you do like, it's kind of sequential process, because the agent observes the state information and then it takes the action, and then you store each of these in an experience buffer. So it happens sequentially. And once this experience buffer is full, then you start training your network. And it could be that like we are not even using like a super big training data set. We have like, for example, if we put it into like how many samples we have, it's just like 1,000 or something. So in the end, like if you try to use GPUs, then you will get the overhead of transferring data over the PCIe, and then you send the data there and the model gets trained, and the model is not that big, and then you transfer the weights back. So it's kind of an overhead. So it really depends how big the model is. And usually what I've seen in literature as well, we don't really need super big models for these state features. So at least at the moment, I don't really buy the thing that we really need to accelerate this on GPUs somehow. Maybe if there is some sort of scenario where you have a super big network that you need for like with RL, and then maybe it makes sense to use like GPU, but at least in our case, we didn't have to.
Okay, thanks, great. But so I think other than this hybrid strategy management, I think personally, I believe reinforcement learning has great potential to optimize the other parts of the system also. So in that case, I don't know, so some multiple models need to learn on the same system, right?
Right.
Yeah, so in that case, I think it could be somewhat useful to have a dedicated reinforcement learning accelerator, not GPU, because it is also shared by the many other applications at the same time, right?
Right.
So my question is, would it feasible? So is there some, I don't know, so would it be very straightforward to implement such a dedicated reinforcement learning accelerator?
You mean for multiple agents, or you mean for a single agent?
But at the beginning, single agent, for example.
Yeah, I think it's possible, because if you want to accelerate, the thing that needs acceleration is only the deep learning part, which is like the neural network training. And
exactly, yeah.
We already have a lot of literature on accelerating like these or any deep neural network. So we can have a dedicated accelerator for that. But like for single agent, I don't really see it makes sense. But in a multi-agent scenario, when you have like multiple agents running together, that makes sense as well. It would be interesting to try it out. But to evaluate like in a real setting, it's quite challenging to do that, I think.
I agree with that, yeah.
Like trying to do it on a real system. So I think that's one of the biggest challenges which I see, the evaluation itself. And for multiple agent, I think it's an interesting direction to do that.
Okay, cool. Thank you very much.
Thank you.
Okay, I think these are all we prepared for today's session, and also this semester's PNS course. Thank you again, Gagan, for great presentation. And yeah, I believe we will likely have the same PNS, same SSD course on the modern SSDs, but I don't think I will lead I will deliver the courses in ETH any longer. But yeah, I will also collaborate, keep collaboration with the Safari Research Group, and we hope we can provide more exciting research sessions and also new background lectures on the SSD. So thank you for joining, and keeping track of our our SSD course in this semester. And take care, and I hope see you guys again. Thank you, guys.
Thanks, Jisung. We really enjoyed the course.
Thank you. Bye.